Thank you so much for coming to our most recent series of NASA Talks. Today we have the wonderful Dr. Kai Goebel. I think I'm pronouncing that correctly. Kai holds an MS and PhD in degrees in mechanical engineering from Cal Berkeley. He's the director of Prognostics Center of Excellence at NASA Ames, right down the street from us, and the tech area lead of discovery and systems health area. Before joining Ames, he spent a decade at GE in the corporate R&D, and he has co-authored more than 250 papers and holds 18 patents in the areas of system health management. You've done a good job. Most importantly, Kai is very, very excited about Germany's recent win in the World Cup.
Indeed.
And he said that we should all feel better here in the US that we only lost 1-0 to Germany. So we should feel good about that. Without further ado, here is Kai, and please save your questions for the end, and we do have a microphone, so please talk into the microphone so the people on the live screen can hear you. Okay, thank you.
Thanks, Mary. I hope nobody's here with Brazilian descent, then the 1-0 thing doesn't quite hold. We already went over that, so we can skip that. But I want to quickly talk a little bit about our organization. We have approximately 60 people who are focusing on this particular subject area. We do most of the work for systems health management for NASA, or at least we're the lead organization. And it is mostly low to mid technology readiness level. We divide the maturity of the technology from 1 to 9 in different stages, and 1 to 7 means anything from conception to prototyping, and then we leave the rest to somebody else to implement and actually use it in a mission context. So what we do mostly is provide a state assessment of systems, and that includes technology elements such as data mining, failure prediction, fault diagnosis, decisioning, physics-based modeling, and quantum computing. So that's all stuff that we deal with in DASH, which stands for Discovery and Systems Health. And the overall idea is to enable resilience of systems and to mitigate off-nominal kind of conditions. I'd like to start out with a definition on the next slides. Then I'll be talking why we care if or whether something breaks, and then talk a little bit about how one would go about dealing with that, perhaps preventing it, perhaps with mitigating something that has already been broken. And I'll give a few examples from the NASA context. So, systems health management. It's the capability to contain, prevent, detect, diagnose, predict, respond to, and recover from conditions that may interfere with nominal system operations. Okay, so it's a long thing. What it means is we're monitoring stuff, and if there are any kind of deviations from what we think how the system should operate, then we want to recognize that, and we want to do something about it. Why do we care if something breaks? Well, when we build or buy or operate stuff, by stuff I really mean equipment, then there is an expectation that it should last for a little while, right? So nobody wants to spend a few $100s on something, or a few thousand, or a few millions on something that immediately breaks. And oftentimes things do last a long time. Sometimes they last even longer than we expect. An example might be, this farming equipment. That thing probably is 60 or 70 years old, and farmers are still using it in the field, and these are extremely rugged and robust and last for a long time. Sometimes things do not last. And an example might be here, this Aloha flight that about 30 years ago or so had an unfortunate mishap where part of the fuselage simply broke off in mid-flight. It just flew off. This is a good argument for always staying buckled in your seats. Unfortunately, a few people were not, so there were a few casualties. That's bad, but this is a clear example of where you really expect the equipment to function, and then you are somewhat unpleasantly surprised if it does not. Obviously, we have lots of other examples where things break that cause inconveniences, or that cause, even worse, loss of life. Everybody has a car, and we have an expectation that we can drive to work, that it doesn't break down, but we all know that they can break down. So we do have somewhat of a throwaway mentality, right? We use something and then we stuff it away. But some things don't really fit too well into that kind of mindset. We are expecting that for certain safety relevant equipment that it actually works well. So in particular, I gave an example on the slide before for transportation systems such as airplanes. You really have the expectation that if you get in there, that it gets you safely to the other side, to the next airport. Similarly with cars or trains or ships, or in our context, rockets, right? So if you fly a rocket, you really don't want that thing to blow up. In particular, that something of concern for astronauts who might be sitting on there. They have an expectation that that thing will work reliably. Power, nuclear power plants. We have an expectation that those things are safe and that they work, and that there are no accidents or malfunctions that cause adverse kind of conditions. These have happened in the past, of course. We remember 3 Mile Island. We also remember Fukushima. If that kind of equipment malfunctions, there's quickly large-scale kind of consequences, and we want to avoid that. Medical equipment, right? If you are getting into the hospital with an emergency condition, you really want the CT scanner to work, or the MRI. You don't want that thing to break down right then and there. So you really need that to work. Another motivation besides safety might be that it is expensive either to replace or to operate. Right? Again, in the context of power, you have these large stationary gas turbines. These are huge. They could be maybe 30 meter in diameter or something like that. And if that breaks down, you cannot operate it. So the operators are very unhappy because it costs them a lot of money, because they operate on very thin margins. And it costs a lot of time to repair it, because if you have to crack open a gas turbine and get to the blade that has a crack or something like that, this is a very expensive kind of undertaking. Similarly with wind turbines, they are oftentimes in very remote places, and they are very tall and they're very hard to get to. And if they fail, that costs you money, not for one to repair, but also because you're not operating it and not getting revenue from the power that you're generating. Oil and gas, similarly, pipelines, drill rigs, mining operations. These are all kind of expensive kind of operations where you want stuff to really work. IT, data server farms, picture here. Networks, you want those things to operate, and that may be something that you're more interested in. You can really accommodate the fact that the whole thing goes down due to the cooling system breaking or something like that. Manufacturing, you might have robotic equipment or machinery. Everything is automated, and it costs you money if that stuff breaks down, again, to repair and also from loss of revenue that it's generating. Security critical equipment. In buildings, residential or commercial, you want to make sure that the security systems work properly, that it monitors your house, that it monitors your property, and if that breaks, that's bad as well. So NASA cares about that in the context of crew decision support in emergency situations. Again, if you are sitting on top of a rocket and you're ready for blastoff, and you get an indication that there might be something wrong, then you have to be pretty sure to either call off the launch or to, if it has already launched, to eject the astronauts. And then there's a very subtle trade-off between the false positives and the false negatives. Right? So a false positive is if you are crying wolf and nothing actually is wrong. That's a really a black eye, right? Because you're ejecting the pilots and you blow up $400 million, and that doesn't look good. However, if false negatives are very unpopular with the astronauts, and it's mathematically not possible to really get both the false positives and the false negatives, or the likelihood of both, down to zero. So you have to find some sort of trade-off, and the negotiations of where that set point is a very interesting one between the operators and the astronauts. You also want to ensure mission completion. You want to make sure that crew can come back, but also if you have satellites that are oftentimes very expensive, hundreds of millions of dollars, you can't really afford to put that into space and then it just doesn't do anything there, simply because something breaks that you didn't anticipate or that you didn't recognize. NASA also cares about cost, increasingly so. There's an environment where cost containment is a big topic. So for life cycle management, one is concerned about life extension, to avoid unscheduled maintenance, to increase uptime, to increase launch availability, to make informed decisions whether to go or cancel an operation, and to, in general, reduce risk with the support of go or no-go decisions. And what you see here is a launch pad. That's the launch pad where the shuttle used to launch. And these are fairly complex kind of beasts. So it's not just that you put a rocket somewhere on the ground and light a fuse and everything goes up. These are incredibly complex constructs that have to work just like any other complex machinery. And ultimately, you can use it also for design improvement, where you feed back the information about the operation and also about the abnormal behavior into the design. Here are some examples where things didn't go quite as planned from NASA. So you see a lot of satellites here. Most of them, there's a few here that we think are on Mars, but we're not quite sure because we lost contact and essentially never were able to recover those. There's a few like this one that had a malfunction and then turned into so-called fail-safe mode. But the fail-safe mode was such that the battery was pointed towards the sun, which then proceeded to cook. And once the battery is cooked, the thing is dead. Apollo 13, we all know about the mishap there. And then the space shuttle also had a few accidents that we all remember. So what can one actually do about it? Yes, you have a question.
So what are the common failures, the common types of fault that cause those failures, fault models?
There are very different fault modes. Some fault modes that happen very often is with the gyroscopes. So for Kepler, or even on the space station, there are some misbehaving gyroscopes, which can be traced down to the ball bearings that have certain issues when you operate them in vacuum, because the lubricant tends to behave very different in a gravity-free space than with gravity. In some other cases, you have communications equipment that malfunctions, perhaps due to the presence of radiation. So you have single event upsets and other kinds of fault modes that cause some issues. You may have shorts because when you're launching something, you have incredible vibration, and the harnesses are rattling around, and it might be rubbing on the fuselage, and something might short out that you didn't anticipate. You may have software faults where you have interactions of different software components that you didn't anticipate because you have some new kind of conditions that you never encountered before, and the software was not meant to handle that, and so it does something unanticipated, and it breaks. So there's really a myriad of different kinds of fault modes, and that makes it also so difficult to anticipate all of them and to take care of all of them ahead of time. That is, of course, the idea, right? That is what you like to do here. You try to design out these kind of fault modes that you know about, right? And here the Rolls-Royce is an example of that, where it was built and then something broke, and then the next generation they built a more reliable one, and then something else broke, and they tried to take care of that, and you end up with this 2-ton beast, right? Which costs you an incredible amount of money, but which is known to be very, very reliable, right? And that's one of the trade-offs then, right? So how much money do you want to spend, and how much risk do you want to incur operating these kind of things? You can also build redundancies, right? Like at this car, where you have sort of the dual tires in the back, where one can blow and you can still actually drive this thing. It doesn't immediately tip over. So it's an easy example of redundancy, but in space systems you have redundancies everywhere. Or oftentimes triple or quadruple redundancy to account for the fact that something might break, but you still need to be able to operate your system. And of course, it comes at the expense of more weight and size and again, cost, right? So each kilogram that you have to bring into space costs you thousands of dollars. So you're thinking very carefully, how much more redundancy do I put on this kind of system? And right now we're going towards these nano or nano satellites, where you really can't afford to have a lot of redundancy, because these are contradictions in themselves. So as an alternative, you could try to recognize impending failure ahead of time through analysis and inference, and then you could try to handle the fault ahead of time, handle your remaining resources, possibly extend the life by reducing the load, by moving up the important experiments that you still need to carry out, or the important maneuvers that you still want to carry out, or doing some other active kind of thing, right? So in general, having the information that something is awry and going towards a bad state is a good thing, right? So here's a picture of, everybody recognizes this was the Hurricane Katrina. This is the path that it was anticipated to take, and certainly knowing that is better than not knowing that, right? Because you can evacuate people and you can take some sort of measures to deal with the kind of situation. So how does one determine equipment health? So here's a cartoon of a rocket, right? And the metaphor that we're using really is one of health, of human health. So what we are doing is we are going and We're trying to actually check out what is the heartbeat of the equipment, right? And then you go and say, okay, that's good information, but what about the temperature, right? So having the kind of dual independent information is even more important. And then maybe I can put a ECG on my rocket and figure out what is the state of health of the equipment. Now, if we stay with the ECG for a moment, you go through a series of steps to analyze the health of a patient. Right? So first you take your probes here, right? And some of you may have already had the pleasure or lack thereof of having to go through that, right? And so there's some gel that is being put on these things, and the person who administers that first checks out whether those probes are working well. Then you have to interpret the signal, right? So you get some wavy curve out of your ECG, but what does it actually mean, right? So you have to interpret what does the amplitude mean? What does the steepness of the curve here mean? How far does it dip down? You know, what is the duration of the pulse and all that kind of stuff? And you can see that there are little symbols here that all have some sort of meaning. Well, once you have interpreted that, you still have to figure out whether that is within normal bounds. And if not, you have to then give some sort of diagnosis, right? The patient is moderately ill, or hopefully not, or something else. Now, given the diagnosis, what is the prognosis? How much longer do you have to live? And then if you know that, suggest some sort of therapy. Well, in systems health management, we do a very similar thing, right? Except that checking the probes, we call a sensor validation, right? Interpreting the ECG signal is called feature extraction. So you're trying to automatically get some information out of your sensors. Next, you detect whether there's some sort of abnormal condition. Is everything healthy or not? So it's sort of a rough evaluation of the health of the patient. Then you do some diagnostics, you do some prognostics, so those terms were essentially adopted, and then ultimately you mitigate the situation in some clever way. Now the trick here is you have to do this on some inanimate objects and some equipment, and you have to automate all of that, right? So there's no person who does all that. It's all done in some sort of automated fashion, and that's where the art lies in doing that. So if we put all that together, then you have here sort of this flow diagram of different steps that we just talked about that you go through in a sequential kind of fashion. And so you pump in raw sensor data, and these could be temperature measurements or vibration measurements, or currents or voltages, or any other kinds of information that you get from real sensors. So from that, you actually then have to extract kind of information after you have validated that the information is actually good. Right? If you have a bad sensor, all the inference really isn't going to help you because it will just produce garbage. You then extract features. I'm going to show an example of what that might be. And based on those features, then you make a determination whether you have an anomaly or not. And the output of that are warnings or alerts that indicate here is some anomalous kind of condition. But it doesn't say what it is. It just says there's something wrong. What is wrong is being done in the next step. So it's the next step of analysis where you figure out, okay, this is the particular fault mode, right? So coming back to your question, you don't just want to know that something is wrong, but you want to know what exactly is wrong, right? Do I have to focus on my gyroscope, or do I have to focus on my communications equipment, or do I have to focus on my payload? And it makes a big difference in dealing with the situation. Then you go into prognostics. You want to estimate, well, okay, something is wrong, and I know that's my communications equipment. When will I completely lose functionality? And that is a function of how you're using the equipment in the future. If you're loading it very heavily, it might go more quickly. If you're not beating on it very hard, then it might last a little longer. And then ultimately, you're doing some fault accommodation, and where you're taking some corrective action, and that can be a very complicated kind of thing because you may have multiple objectives that you're trying to satisfy at the same time. And so now we're getting into optimization routines and oftentimes multiple objective optimization where you end up with a large number of optimal solutions, and then you still have to select one of those. All right, so let's go through a quick example for each one of those. I think that it might make it a little bit more clear what we're talking about. So in sensor validation, you have some data from some sensors, right? So these could be pressure sensors and flow sensors. And you go back to the physics, and one could, for example, build some analytical redundancy where you know that pressure and flow are related to each other in some sort of fashion, and the pressure upstream of a pipe is related to the pressure downstream of a pipe. And if you have a change in the pressure, then that has to be correlated to how the pressure is upstream based on the physics of the system. And one can build some sort of analytics that describe how the readings are expected to change if you have certain changes in one part of the system. and so it can be expressed with a few equations, and then one would detect if there is an inconsistency, and you flag that kind of sensor and said, okay, I'm not going to trust that one anymore. I have to rely on the other ones. And I can still continue my analysis, but I have weeded out the bad sensor. And that is actually an important step in the overall concept, right? Similarly to the ECG, you don't want to perform your ECG with some bad probes. It just doesn't make sense. And here it's important that is done automatically because there is nobody standing there. There's nobody standing on the wind turbine, checking those probes on a daily basis or on an hourly basis. It has to be done automatically. So next, you have to extract features, right? So the question here is if you have a bunch of data points, where you have, this is the magnitude of something, maybe pressure or temperature or vibration, and here you have time, you get these data points in, what do they mean, right? Where is the information? And there's a lot of signal processing techniques that can be employed to really pull out information out of raw data. So you're not just looking at the magnitude, but which of course can be important information, but there's more than that, right? You can let's see. You can extract information also in the frequency domain, or in the chaotic domain, or in any other domain. So you can transform the data into a different domain. Fourier transform is an example thereof, or wavelet transform. And then extract features in that kind of domain. So let's see. So we want the features to be explainable in physical terms, mathematically definable. We, of course, want them not only to look pretty, but have some sort of meaning with regards to the fault that I'm trying to diagnose. It should ideally be uncorrelated with other features. It should be insensitive to extraneous variables, and also not too expensive to measure if I have limited computational resources on my asset which may not be as much of a concern if you have a ground-based systems, but if you have a space-based system, again, if you want to put a supercomputer on a nanosatellite, that's not going to be so easy. And then, of course, you can derive features of features where you're extracting information from the features, or you're combining them in some sort of smart fashion. And there's a few examples here where you have various statistical moments or combine them in some other fashion. And one can also automate that, so you don't need to necessarily know all of that ahead of time what you want to do. You can have learning algorithms or machine learning algorithms that explore the space of features and find new features for you. So you could use genetic programming or genetic algorithms or other optimization tools that find combinations of different features. And I already talked about Fourier and transfer form. So now we have only gone to the point of actually deriving features. Now I actually have to make a determination whether something is anomalous or not, right? And how would I do that? So the question here is in this data set, I'm just looking at the last 4 data points. Are those in the normal range or are those abnormal? So who thinks these are normal? Who thinks they are abnormal? Okay, I need a brave soul here. And who has no opinion? Okay, all right. Okay, yeah, maybe it's hard to tell, right? So we don't really know. So one example of a tool that one could use here, and there's literally hundreds of them, is the rank permutation test, which transforms the data in some sort of ranking space and then performs a hypothesis test in that rank space. So you determine a null hypothesis, which is the data are abnormal or not. Then you choose some sort of test statistics, which in this case here is the sum of ranks. Then you compute the test statistic for original observations, permutate the observations, recalculate the test statistic, and repeat that 1,000 times or so. And then you either accept or reject the null hypothesis that this is normal data. And if you do that, many times, like here, right? So you just sample your space before those. You do this over and over and over again, and you compare those data that you sample with the ones that you're investigating. And then after you do this 1,000 times, and I'm not going to do it many more times, I hope, you calculate the statistics, and you look where are your data points here, which is where the line is. And you can see that most of the data actually is on the right side of that curve. And if you calculate that, it turns out that there's only there's a 99.3 almost % chance that this data is not normal, right? Which is not obvious when you look at the data as they were originally. They were sort of within the bounds, but they were just slightly clustered outside. And so that is an example of how one could make a determination that data are abnormal or not. Obviously, where you put the threshold is completely up to you, right? So if you want to have a 99.999% confidence that something is abnormal or not, then you would have to wait for the signal to become more clear. So now that we know that something is not normal, we want to go and analyze the data with regards to the fault mode. And that can be done through a number of different ways. One would be to have some sort of inference systems, which could be implemented through a rule-based system where you have different kinds of rules, where if A is B, then C, right? And you could have a number of different rules, and you could see whether any of those rules are triggered, and then you could make an inference with regards to the particular root cause. You also have to deal with the fact that some of the data may be not completely crisp, or that the fact that the data are very, very close to a threshold just on one side of it may result in your diagnostics to fluctuate a lot. And so you have to deal with uncertainty in some fashion. And there's different ways to do that. You could do it in a probabilistic sense. You could use fuzzy logic. You could use a number of different ways to deal with uncertainty. And then, the term fuzzy logic is sometimes used to express that nothing serious is being done, but in fact, it is a methodology that you have to step through, and there's very clear rules how to deal with the information in some specific way. And this just shows an example of that, where you have some facts where X is A and Y is B, and a rule, and you check whether you have to come to some sort of conclusion about the result. And this is just a visual of how you go about that, and you end up with geometric constructs, and you have to take out some actual crisp decision out of that. There's some methodology that you go through to accomplish that. Okay, now that we know that my communication system is bad, now I want to know at what point does it fail so that I have lost complete a function of that equipment. And that is done in prognostics. Now you're trying to estimate how much time do I have until that happens. And so there's a graph here that shows that, where you have time here and the health here, and the health deteriorates oftentimes in some sort of non-linear fashion. And you're predicting at different time points how much time do I have until I reach a threshold. This would be my end of life threshold. How much time do I have until that happens, right? And so that is done again using some mathematical tools, where you're not just waving your hand, or you're using some straight line extrapolation and saying, okay, maybe here in sometime in the future. You have to account for the fact that your system may behave in some nonlinear fashion, which again is driven by the physics of the system, and so you have to encapsulate that in some smart fashion. That could be done either by using data. So you could have a data-driven kind of approach where you have observed your system or a fleet of systems many times, and you have all kinds of trajectories that inform you about how the system deteriorates, and then you can build, again with machine learning tools, a representation of the deterioration over time. Or you have to build a model that is based on the physics of the system that you're using to express the expected change of the degradation of the system. And that you have to do when your fleet is not very large, right? So that is something that we at NASA have very often. Your fleet size is not 20,000 or 100,000. Sometimes it's one, right? And so you can't blow up 35 test rockets just to see what happens when my case cracks. That is too expensive. So you have to, or you cannot wait for that to happen either, right? So really have to wrap your head around what is actually happening at the physical level when there is a crack in my rocket casing. How is that growing as a function of the internal temperatures and pressures of the rocket. So another example is here on the launch pad that I showed earlier. You have some, in these spheres here, your liquid propellant. It's oxygen and hydrogen. And so there is a 1.5 kilometer line here to this oxygen tank. And then if you go out, here's the launch pad. And on the other side, far on the other side is the hydrogen. And you want to keep those two really far apart. And you want to wait until the very end before you get them close together. Because it's, for obvious reasons, it's very dangerous. So you also want to make sure that any of these pumps and valves are working, right? Once you actually say, okay, system is a go. Okay, now we're pumping, 100,000 liters of liquid oxygen or so into the external tank of the space shuttle or whatever vehicle you have there. You don't want to get into a situation where you say, oh, sorry, my valve is stuck right now. Can we scrap the launch? I mean, that immediately costs you a lot of money and makes a lot of people very unhappy. And your launch window may no longer be open because of weather or other kinds of constellations. And so it really needs to be available when you need it. So you need to have an assessment of the goodness or of the health of these kinds of pieces of the equipment. And so here are some examples of valves. I'm not sure how well you're seeing that, or pumps that are being used. Some of them are pretty old. Some of these tanks have been used during the Apollo area. So that was a long time ago. So the pump that I just showed can be modeled, right? So here's just a cartoon of that. But fundamentally, what you have is just a plug here, and here's the pipe with the fluid flow, and you can, if the plug advances, then the fluid flow is interrupted. If it goes up, then obviously something can flow, and you do that by opening the valve, by pumping in some pneumatic air in here that lifts the piston up against a return spring, and there's a port up here that opens and allows the air to escape. And if everything fails, this particular valve has a fail-safe of closed, right? So the return spring then forces the plug down, and it interrupts the pressure. Now, seems extremely simple, but if you have some wear here, then you have some leakage along the plug. Or if you have a wear along the piston and the wall, that's no good, because then not enough pressure can be built up to open the valve. Similarly, if the return spring gets weak, or if there's some leakage across the top port, you have some consequences that you somehow have to deal with. And so even for a very simple component like that, you have half a dozen fault modes that you can model and that you can account for, and that one can use. One still has to figure out what is my end-of-life criterion, and you can go back to the specifications and say, okay, the valve has to open or close within a certain time frame. So let's say the valve has to open in 5 seconds, right? So, and usually, if everything works well, it opens in 1.5 seconds. But as things are degrading, you see that it opens slower and slower, and eventually will no longer meet your functional spec. That's just to say that you don't have to wait for something to explode or something catastrophic to happen to define a failure. What we actually need is a mathematically quantifiable threshold that we can work towards, and that we can define how far away are we from that threshold. And that's actually very important to ultimately calculate what is my remaining life. And then you go into your modeling. You express your valve state through positions and velocities and gas mass above and below the piston. And then you do some state derivatives and inputs. Has anybody seen anything like that before? All right, we have a few engineers here. Excellent. And then you do physics 101, right? So you have some piston movement and that kind of stuff. And then you do physics 201, you express your gas flows and that kind of stuff. There's nothing magic about here. It's all textbook stuff, right? But it actually gets employed to express the expected behavior of your system. And so everything that you learned in physics in high school and later in college actually gets used here. And then you go and look at what kind of sensors do you have. And from that, you can then model what is your expected behavior of your system, right? How should your valve open and close based on the expression of the physics. And then you can also model damage. So you may have increase in friction, or you may have a decrease in friction due to wear, and all that then ultimately, which is expressed down here, leads to changed characteristics of the opening or the closing of the valves. And that is expressed here, based on the particular fault mode. You see that these curves change as a function of the cycles in this particular case of operating of the valve. And then you still have to deal with, okay, now that I know what my state is now, how will it change in the future? And so you have to extrapolate that out into the future. And one particular technique that can be used is called a particle filter. Many of you may have heard of a Kalman filter. A particle filter is something like that. So it's not a physical thing where, like in your vacuum where you have your filter. It's a mathematical tool. And I'm not going to go into details of how to use that, but the whole point is that you are going into the future with different kinds of possible paths to then express your end-of-life prediction through a probability mass function, in which you can approximate with the probability density function. So there's not just one point that you're getting, unfortunately, because you may have a lot of uncertainty due to your sensor measurements, or your model is bad, and your future load predictions. So your actual remaining life will be a curve, will be or it can be approximated with the probability density function. But you can still choose, either I choose here the median of the curve, or again, if I want to be conservative, I can be on that side of the curve and take the extremely risk-averse point. But the point of that is you buy yourself that much time to actually do something, right? So you don't have to wait until it actually breaks, and you don't have to replace the valve on a conservative schedule, every 10 cycles. You actually know with high confidence that you can operate this thing safely that many times without an expectation that something bad is happening, right? And that's the beauty of that approach. And then, of course, you're repeating that. As you're using it, you're collecting more information about the current state of health of the system. You're updating your expectation of what is happening. And if you did everything right, then this curve actually will not move. You're just moving through time, and the PDF here will just get steeper and more narrow because you're taking out more uncertainty. And then you can calculate your performance, and then ultimately you do something about it. That is, again, you're using different kinds of techniques to go about that. And what you're doing with information, you have 50 cycles left. is different than if I tell you that I have 5 cycles left. Or if we express it in time, if I tell you that your system will break in 30 milliseconds, there's no point in scheduling maintenance to accommodate that, right? If I tell you that your system will break in 3 months, well, now I can schedule maintenance when it's convenient for me. If I have the guy go out to the wind turbine in 2 months anyway, well, maybe he should look at the other one next to it, and that saves me money, right? Again, you know, I can, again, if I have 30 milliseconds left, I go immediately into a fail-safe mode, reflexively. If I have 3 hours left, I can think about mission rescheduling or replanning, and again, you know, do the right kind of thing. All right, so these kind of concepts we implemented here on our Rover concept. This is sort of the monster truck of the Rovers, and we use the Nexus S for part of the instrumentation suite. You know, obviously, as you know, it has a whole bunch of sensors on there, which is extremely convenient. It also has communications, wireless communication and storage on there. And we have taken advantage of that. You just plop that thing on there. And in principle, you could use that for all kinds of different things, right? Not just for rovers, but you could put it on many different types of equipment to enable the kind of reasoning that I just described. In this particular case, the fault modes of interest that we're interested in were motor windings deterioration, battery charge depletion, capacity degradation, some parasitic electrical load, increased mechanical friction, and we built some fault injection mechanisms onto the rover. So you know, sometimes you have to wait a long time until something bad happens. So here we, since we didn't want to wait 30 years for, you know, the bearing to go bad or something like that, we helped things a little bit and built in mechanisms that put in a parasitic load, or that which resulted in the battery discharging faster and degrading faster. And so it's a nice validation tool that allows you to test out different kind of concepts. Also for mitigation, which are important in sort of an autonomous context, right? So if you have a rover go around and it experiences some deterioration, well, what do you want to do, right? If you have a rover, I mean, this is our self-driving car fundamentally, right? So if your self-driving car is degrading, well, are you going to do something about it or not, right? And the right answer is yes, of course I want to do something about it, right? So what do I want to do about it? Well, and again, it depends, right? And how you go about that has to be done in a rigorous, mathematically rigorous fashion, and which can be described, for example, using different types of optimization techniques. You have to build a simulator into your tool that explores different kinds of options, of mitigating options, and that then implements the right solution. So on a self-driving car or rover, it could be, you know, don't go 75 miles an hour, go only 55 miles an hour. It buys you enough time to actually get to the target. Or it could be, well, you know, we have to cut the scenic route short, and we can't do these waypoints. You know, we have to cut a few off and get you back earlier. But at least we know that it's important to you to get back, and we can satisfy that particular constraint, and so on. And so that's shown here, where, you know, you have a different waypoints. This is the route that we wanted to do. Here we found that there was a fault, and the mission replanner then said, okay, you know, I have to cut out this waypoint here, and I'm going straight back. But I'm going back with some margin that allows you to complete the mission. Some examples here, you know, what we use, the techniques that I just described for rocket engine test stands, for robotic space flights, aeronautics, right? So the first A in NASA actually is aeronautics. So we do a lot of work with aircraft and other kinds of things that fly within the atmosphere. Composite shrouds, ISS, and etc. All right, so what did I just show you? We use system health management and we understand it as a systematic engineering discipline that is used to monitor systems to determine whether things run expected or whether and when they might break. And the core elements within that suite of techniques or that umbrella are monitoring, modeling behavior, recognizing anomalous behavior, predicting time to some sort of boundary condition, and ultimately also mitigating that. Some of the remaining challenges that we still have, not everything is done, are to implement learning and adaptive systems. Right? So for us, space is still the final frontier. We actually don't know what's out there and how systems will be behaving. So we have to build in a system that can adapt to those unanticipated changes and do the right thing. Software complexity. V&V and certification, that may be something that resonates with you as well, is something that is increasingly a challenge to make sure that our complex systems will be behaving properly. Uncertainty management. So nothing is deterministic, right? Everything has uncertainty. How do I properly express and represent and encapsulate my uncertainty and deal with that in a decision-making context? And then ultimately decision-making itself, right? Tie the information back to the benefit that you're trying to generate, right? Which could be completing the mission or bringing the astronauts safely back. And there's oftentimes competing kind of objectives that have to be properly dealt with. And with that, I would like to close here. And if you have any questions, I'd be happy to answer those.
So what are some strategies for dealing with software failures where the things that go wrong might not be as predictable as a mechanical failure where you know what the faults are going to be? Right.
So obviously, you want to, again, design out as many as you can. We think that software health is one of the next really emerging important topics. We have already looked into that. You can monitor certain things, right? You can monitor the number of threads or your communications, and you can monitor your memory usage and all that kind of stuff. And relate that back to the application that you're running and have some sort of feeling for whether things are right or wrong. So in that sense, actually, you could use some of the concepts that have been that I explained here in the mechanical kind of context, also for software. That alone will not get you there. So what we have to do is explore how you would go about autonomous V&V, actually. Right, so as you are have to implement new routines on the fly, you have to perform V&V on the fly also, and so that and there are some formal methods that one can explore to tackle that, but that is definitely a not completed topic yet.
Okay, so how does your onboard health monitoring hardware look like? If you want to do the autonomous V&V,
how does it what? Sorry.
The onboard the health monitoring hardware.
Yeah.
Because everything is automated.
Right.
So what kind of processors? How many processors are using to run your health monitoring?
For conceptual things, you can use whatever you want, right? But if you want to fly something in space, it has to be rad hardened, and usually you run some processors that are 20 years old or something like that. So you're not going to get the state of the art for that.
the operations you show looks like pretty computation intensive if you want to do that on board, right?
Yes, and so we will have to push for making more resources available on board for these things, and we expect that they will. I mean, that is clearly the expectation is that more functionality will be assumed through software, and it's exponentially growing, and I don't see that the curve will be flattening anytime soon. Well, thank you very much.